This is the Interact Centaur rover from ESA. It can be remotely controlled from orbit by ESA astronauts. NASA has its own version. They are one of the tools for future investigations on Mars. The proof of concept in Earth orbit will make it a reliable tool on Mars. Astronauts can maneuver the robot to a test table, then perform very fine operations with a number of tools and devices. It could even help assemble hardware and habitats on the Martian surface while astronauts orbit overhead. NASA's Curiosity rover continues its epic journey across Gale Crater, covering over 14 kilometers in its 3 years of operation. It will soon be replaced by its smarter big brother, Mars 2020 rover. Built on the same configuration, the 2020 rover looks strikingly similar to Curiosity with some improvements. A landing hazard redirect feature to avoid any rocky landings, new wheels and treads for better climbing, audio microphones to hear what's going on, and a rock core sampling drill. One of the main goals of the Mars 2020 mission will be to determine the potential habitability of the planet for human visitors. Scientific instruments on board include an advanced stereoscopic imager, environmental sensors for temperature, wind speed and direction, pressure, humidity and dust particle size and shape. Pixel is an X-ray fluorescence spectrometer for chemical analysis of Martian soil. RIMFAX, a ground-penetrating radar to study subsurface geology, and Sherlock, an ultraviolet laser spectrometer for the study of fine-scale mineralogy and organic compounds. The final instrument package is MOXIE, a technology demonstrator designed to generate oxygen from the carbon dioxide in the Martian atmosphere, a critical piece of kit if humans are going to survive on Mars. It will generate oxygen for fuel and breathing. Mars's atmosphere is predominantly carbon dioxide, plus trace amounts of argon, nitrogen, oxygen, and carbon monoxide. Its mean pressure is 600 pascal, that's about 0.6% of Earth's air pressure at sea level. So another vital piece of equipment is the spacesuit.
In the future, I'm looking forward to spacesuits that are much more of a tool for the astronaut, that is more integrated with the human, and is less of an encumbrance and more of a help.
Several spacesuit designs are underway. There are many specific requirements. The flexibility to walk and move on a low-gravity planet, for example, and the ability to bend down and pick things up. They must also be able to illuminate the way forward. Ease of access for donning the suit is important, as are clearly a pressure garment and thermal insulator for the low pressure and temperatures on Mars. The latest prototypes, like the Z2 and the PXS, are going through extensive development for surface use. The Z2 meets the walking and flexibility requirements. PXS is a more traditional style of suit, but also quite flexible.
My main responsibilities on this spacesuit is the suit control assembly, and that's the box that sits right here on the front of the suit. And it allows the crew member to control their life support components, such as their cooling and their pressure, and it also controls a lot of the electronics, such as the radio and the volume, and they can see some of the data that's coming back and forth from the suit computer to that display. So one of the great things about this job is that after designing the box, I'm able to get into the suit, since it's one of the smaller sizes, and we can actually see what the limitations are, with my own hands and eyes, and not just hear that secondhand from another test subject that would be looking at the same data. And then to take that back and then to go build the next prototype and incorporate the changes that need to be made so that it works better the next time.
Another critical element for surviving on the Martian surface is power. The sunlight reaching Mars is just a little more than half of what we receive on Earth. In addition, there are regular dust storms, and solar power may not be sufficient of itself. It will have a role to play, but other sources of electric power may be required. NASA has been developing fission power plants for such requirements, working on 2 systems. The less powerful technology demonstrator unit for spacecraft and surface operations requires watts of power numbered in the tens or 100s. Kilopower addresses the need for surface power from 1 to 10 kilowatts for human habitats and scientific exploration in the harsh environments of Mars and beyond.